Okay, so this video addresses the following question that a lot of people have when they take Calculus 2. Is what is the integral of e to the x squared dx? So in particular, they want to know it in closed form. We want a closed form. Okay, i.e., so I mean, there's a very easy way to do this integral, right? And you can just expand it as a power series, right? So n is equal to 0 up to infinity. So you have x to the 2n over n factorial like this, dx. And then you just kind of integrate term by term. And I'm not even going to write the interchanging of summation and integration, and 2n plus 1 over n factorial. Okay, so this thing here is not a closed form. All right, so what we want to do is we want to write it in terms of like sines, cosines, logs, something like that, like functions that we already know. All right, and so the spoiler is that there's kind of a theorem is that there is no closed form. Okay, you can't do it. So this is Liouville. And this is from the 1830s, I think 1839. And it says that there is no elementary closed form for this integral. Okay, so Liouville, I'm just going to anglicize. So Liouville actually proved a lot more than this, and I guess I don't know what to say about this, but okay, one of the things that I do have to say is that we have to make sense of what this means. So I'm going to punt on this for a second, and then kind of show you how this works. All right. So let's state what actually is a criteria, and that'll give us more integrals, and then we'll kind of like check that this works in a particular case. Okay. So so let me give the theorem here that's going to work for us, and then we're gonna apply it to this example. Criterion. Okay, for integrability. So an integral here, the integral, and we'll do f of x e to the g of x dx for f of x and g of x elementary is itself elementary, meaning that it can be expressed in terms of basic functions. Okay, and again, I have to define what that means, but it's going to contain like sine, cosine, log, exponentials, tangents, algebraic functions, all the things that you want. I mean, maybe depends. Okay, all the basic things. Okay, all the things from Calc 2. So this integral is elementary if and only if. So there exists some rational function. So this is a quotient of two polynomials, right? Satisfying a particular differential equation. And here's the differential equation. It's mu prime of x plus mu of x g prime of x is equal to f of x. Okay? So we're looking for, so if you have these two things, if you have an f and g, this integral will be able to be written out in elementary terms if and only if you can find a rational function, quotient of polynomials, such that this thing holds. Okay, so let's do there's two ways. There's two directions of the proof. One direction is really easy. So let's do the proof of the easy direction. Okay, and this is just essentially the fundamental theorem of calculus. So suppose such a mu exists. Okay, then so then what we'll do is we take some sort of, I think we do this. So let me write it over here. So we take a derivative of, okay, so essentially what we're going to write is we're going to write the integrand as a derivative of something and then apply the fundamental theorem of calculus. Okay, so I think this is mu of x e to the g of x. I think this is the correct thing that we're supposed to do. And so what do we get? Mu prime of x, so we do the product rule, plus mu of x, and then we do g prime of x e to the g of x. And this thing is equal to, well, okay, so this factors, this part here factors out. Okay, and you're just left with you're just left with, okay, so you have this green stuff, which is this green stuff here. Okay, so that's just equal to f of x e to the g of x. Okay, and so then the integral of a derivative, so now we have this derivative here, and the integral of a derivative is the thing under the derivative plus a constant by the fundamental theorem of calculus. Okay, so all right, so this is kind of, all right, if you have this, you can do it. We'll talk about, in the next video, we'll talk about what it means to be an elementary function, and then we'll talk about the proof of this. All right, so let's do the application first, okay? So the application. This is kind of the fun part. Liiouville's criterion. All right. Okay, so the example that we're doing is, so we're doing this example of e to the x squared dx. Okay, and this is the integral of f of x e to the g of x dx. Okay, so f is 1, g of x is x squared. All right. All right, so then our ODE that we have, right, so this kind of like integrating factor thing says that mu prime of x plus mu of x g prime of x is equal to f of x. Okay, so this equation here is that mu prime of x plus mu g prime, this is 2x, and this is 1. Okay, so this is the differential equation that we need to solve. All right, I guess it will be convenient for a moment. Let me just kind of work with this for 1 second. All right, one more second, and then I'll go back to this thing here. So what are we looking for? So we're looking for mu of x that has the form p of x over q of x. And then these things are polynomials. So this one here, the numerator and the denominator. All right, so let's plug this in. So plug this in. All right, so we do the quotient rule. P prime of x, q of x minus q prime of x, p of x, this is divided by q of x squared, plus p of x over q of x. Okay, I'm going to keep the g here, f of x. All right, and so, all right, so then we're going to clear denominators. So I'm just going to kind of swipe back and forth real quick. So we have, so we'll multiply by, so this q squared here, we're just going to multiply by q squared everywhere. So this is going to get, so this is going to get a q squared. This thing, this goes, oh, let's see. This part here, oh, let's see. So this part here goes away and we just get a q of x, and then this part goes away completely. Okay, so then let me just write it over here. So we get p prime of x, q of x. So I'm just kind of preparing this right now because I'm going to do some more examples after this one, and I just want this formula to just kind of do it easier. So that we have p of x, q prime of x, g prime of x, and this is equal to, oh, this is not an f here. This is a p. Okay, and then we have f of x, q of x squared. Okay, and now what we'll do is we will factor it. Okay, so we'll put everything with a q on one side. So, let me go back to black. Okay, so everything with a q on one side. So this has a q. This is not right. This should be a q. Okay, this has a q, and this has a q. Okay, and so this tells us. So let's bring this term over to the other side, and so we get q prime of x, p of x. So this is equal to what? P prime of x. Okay, so p prime of x plus p of x, g prime of x plus f of x, g of x. And then this is all times, sorry, f of x, q of x. So this is a q. Q of x times q of x. All right, so this is our nice formula. All right, and then so we'll come back to this. All right, and then let's go over here and let's go back to this particular version. So all right, so what do we get? So so here we have that g prime. So this thing this is a so for a particular application, this is all right. So what do? I did that in red. Okay. So we have q prime of x, p of x is equal to p prime of x plus p of x. This is a 2x. Okay, let's write this a little nicer. 2x p of x plus, so we have f was 1, and then we have q of x times q of x here. Okay. So let's make some assumptions on p and q real quick. Okay, so this is the formula we get. Okay, this is the formula that's going to give us a contradiction. All right, so I claim this is impossible. Okay, this is the formula for e to the x squared. Right, and so we are assuming that this p and q here, that those are polynomials. Okay, and then what we'll do is they're going to be co-prime. This is kind of the important that we're going to get this, and then q is not equal to 0. So this means that it has no common factors. So by the fundamental theorem of algebra, right, if we do a polynomial over the complex numbers, it can always be factored into monic, so x minus some lambda to some power, right? And so we're assuming that there's no powers in common, and then we're going to derive a contradiction, right? So we have this thing, and so the idea is that the zeros of this and the zeros of this need to be distinct. So the zeros of these two polynomials are distinct. Okay? So what are we doing right now? We're deriving a contradiction. Okay? So, all right. So the other thing that we know is that this thing here, Okay, so q of x. All right, so if we can always write this as the sum of so I'm not q but q, so it has some multiplicity, so it looks like aj x minus lambda to the j. Okay, and this goes from j is equal to the multiplicity up to the d. So this looks like x minus lambda thing times some crap here. Okay, and so this is the multiplicity at x is equal to lambda of, so this is the multiplicity of the 0 of this. Okay, so we can have this. If this is the multiplicity, using this form, you can see that the multiplicity of q prime, right? So this this one here. Okay, so this has to have multiplicity if this is multiplicity m, this is multiplicity m minus 1. All right, and so this thing looks like m minus 1 times something. All right, some polynomial that's kind of like over here. Okay, and it'll be degree 1 less than q. Maybe I should have said this too. Is that, you know, what we're doing right? Okay, let me just do the proof. Okay. Okay, so we know that on this side here, right, there has this has this big factor here. Okay, so that means that x minus lambda to the m divides q prime of x, p of x. Okay, but this part here only has multiplicity, you know, x to the lambda to the m minus 1 dividing q prime of x, right? It doesn't have a bigger power because we took a derivative, right? All right, but so in particular, x minus lambda to the m does not divide q prime of x. All right, so this implies that x minus lambda divides p of x. Okay, this is a contradiction, right? Because we assume that they were co-prime, right? That they had no common factors, and so that that gives the proof. All right, so we proved. So we have proved there does not exist some mu of x in c of x satisfying Liouville's criteria. All right, hence this thing here, this integral, the integral of e to the x squared dx is not elementary. All right, so this is a genuine new function, right? That isn't one of the Calc 2 functions. That's the point. All right, so let's see if we can do, let's do another example. Okay, so I'm just going to do some more examples of I was like, oh my god, am I not recording? Okay, of this thing. Okay, so let's do another example. Okay, and then this example is going to give a bunch of other examples by like integration by parts and by u substitution. So I'm just going to give 2 examples like that. So this integral here of e to the x over x dx is not elementary. All right, so this one's a little bit more involved, but okay, so to prove this, we use Liouville's criterion. All right, so so we have f of x in the previous statement. F of x is 1 over x g of x is x. Okay, and then we're looking for, okay, I was going to write out the equation again, but we already have this form here. Okay, so is there a way to like copy this? Scissors? There we go. Oh, didn't mean to do that. All right. All right, here we got our equation here. All right, let's kind of clean it up. All right, so we have our equation, and let's just fix it real quick. So this f here, so this is 1 over x, and then this g, this is 1 in this particular case, right? So then we can multiply through by x to get q prime of x, p of x times x is equal to q of x, okay, xp prime of x plus xp of x plus q of x. That's a q. Okay, so we're going to do the same thing. So we suppose that that P and Q, the GCD of P and Q is 1 and Q is not equal to 0. All right, so all right, so really I mean by this, the ideal generated by these two things is the unit ideal and the polynomial ring. All right, so let's see what happens, right? So there's kind of two cases, right? If Q, the first case is that if there exists some lambda not equal to 0 such that Q of lambda is equal to 0, then we just kind of run the exact same argument. Run the same argument. Right, so here, what do we get? So this thing, so we get some power of x minus lambda to the m, dividing this thing. It has to divide one of these pieces, right? Each x minus lambda has to divide one of the pieces, and there's only so many pieces the q prime can have, so it has to divide the p since it doesn't divide the x. Okay, so then the other case is that is if lambda is equal to 0. All right, so let's do that case on the other. So in particular, so what I'm saying is that if q lambda is equal to 0 implies lambda is equal to 0. All right, so let's do that case. So what we're saying here is that the only root of q of x is 0. So that means that q is going to be essentially a power. So we can assume one of them is p or q is monic, and so we'll take it to be q for right now. So we can take q. So this looks like x to the m for some m. All right, and so what does this equation become? Do I have the equation? Ooh. Very nice. Okay, so we have this equation. Okay, and I'm just going to replace some pieces here. Right, so this piece here, this becomes, so I'm using this, here. So I'm using this formula. This is x to the m. We have this f and g. Okay, so it's not quite the formula we want. This was 1. And then this, so we had an x over here. You get an x, and you get an x, and you get an x. And put the x over here. And this f goes away. Okay. So then this looks like that. And then q, this thing goes away. So what's the derivative of this thing? This is times m, x to the m minus 1. All right, and then what happens is that this here cancels with this, right? And we get a new expression that says that mp of x is equal to xp prime of x plus p of x times x plus q of x. And q of x we know. X to the m. All right? Okay. So now we have the same issue, right? This is x times p prime of x plus p of x plus x to the m minus 1. All right? So this tells us that x divides p of x, which is a contradiction. And that would prove that they have, they again have a common factor, but now the common factor is 0. All right? So, so the conclusion is, so we conclude, so the conclusion is that this integral of e to the x over x dx is not elementary. All right? All right, so this is, this is cool. All right, so let's kind of beef this up a little bit just to do some more fun examples. All right, so let's do an example. So let's do example. Okay, so so the logarithmic integral. Okay, so logarithmic integral is a famous integral that appears in the prime number theorem. So what's the prime number theorem say? So the prime number says that the number of prime numbers less than less than x grows like x divided by log x, which is asymptotic to, I think the logarithmic integral. So this is an integral over 1 over log. And there's a famous story that that he was actually looking at a table of the primes, and then you can look at the digits, and essentially log of anything is like the number of digits that appear really in a number. Okay, that's where this idea comes from. Anyway, that has nothing to do with what we're talking about. This is the logarithmic integral. This thing, sometimes this is called Li of x. So it is not. Okay, so then you have to really do something like 1 to. Okay, maybe when I do a big X here, is not elementary. Do I want to do 1? I don't think I want to do 1. Maybe E. Right? Because if you did 1, there'd be a thing, a 0 down there. Okay? So this is not an elementary integral. So this function can't be expressed in terms of the Calc 2 things that you want. Okay? And so how do we do this? So let's do, all right, so let's do the proof. Okay, so let x equal log of u, all right? And then what we'll do is we'll use this integral of e to the x over x dx. And so this is the integral of e to the log of u over log of u. And then here we'll use dx is equal to d of log of u. And this is du over u. All right, so you take the derivative, which is 1 over u, and then you do that. So this is du over u. This thing just becomes a u here. So these cancel, right? And this just becomes the integral of du over log of u. All right, so if this had some form that we could integrate it, we could just kind of plug things in, and we'd get an expression for the logarithmic integral. We can't do that. So this shows that you know, since this one's not elementary, this one's not elementary. Okay, let's do another example. Right, so let's do an example. So the integral of log of x dx is not elementary. Okay, we're again going to reduce. So this one was kind of a U substitution. This one is an integration by parts. So U, so this is 1, and this is log of x. All right, so we have these. And then, so this gives us that du is 1 over log of x. And then we do the chain rule. So then we do dx over x, right? And then dv, so this means that v is equal to x, okay? All right, so now what do we do? So we have this integral here, log of x dx, so log of the log. And so this is uv minus the integral of v du, right? Right, and so this is equal to, okay, so u v did I do this right? So v is 1. So we have x. So is this really a log? U is log. Okay, whatever. So this is 1 over, I think maybe I had this computation on it. So 1 over log. And then v is x, so x over log minus the integral of, so now we do du and v, so we have x, so we have x times 1 over log of x, dx over x, okay? And then these two things cancel. And so this brings us back to the dx over log x, the logarithmic integral. Okay, so I'm really flipping for people who are wandered into this video. This is, log and ln are the same thing. Yeah, I'm just using both of those for the natural logarithm. I was trying to be consistent and use ln, but anyway. So this is again the logarithmic integral, which is not elementary. All right. So elementary. I need to explain what those are, and I'm going to do that in the next video.